this chapter, we're going to explore the calculus of exponential and logarithmic functions. In this lesson, we'll be looking at the derivatives of exponential and logarithmic functions in general.
Okay, everyone. In this particular lesson here, we're going to be taking a look at the derivatives of logarithmic and exponential functions. We're going to kind of wrap up the material that we've been introducing here. We're going to kind of look at all the possible little derivatives that you can get in this particular chapter here. So just recall, okay, what we looked at before here. If y is equal to b to the x, then we know then y primed is going to equal b to the x multiplied by the limit as h approaches 0 of b to the h minus 1 over h. Okay? We're going to come back to this in a little bit here, and that implied that there was this number, therefore, that was a very special base, e, that we get this y equals e to the x, and then y primed is equal to e to the x, because e was that very special number where this particular limit here went to 1. And then we explored a little bit of what that implied. Okay, really, really special function, okay, because of the properties of e, because this is what occurs here. But having said that, still an exponential function. And that what this did is that created for us, or implied the existence of a logarithmic function here, y equals the natural log of x, okay, which is the inverse of this. Again, really, really special because it is the inverse of y equals e to the x, but at the same time, still just a logarithmic function. So now what I want to do here is we're going to consider this function here. So consider y equals the natural log of x here. We're going to take the derivative. Now, to find its derivative, okay, to find its derivative here, what we're going to do is we're going to change its form. Okay, because it might not be clear how to do it in this form. We're going to change it, its form here. So to find its derivative, change its form. And so what we mean by this is we're going to start with y equals the natural log of x. But what we're going to do, because the inverse of the exponential has two different forms, what we're going to do is we're going to look at the exponential form of this. So the base is e, it's equal to y, so this is going to be e to the y is equal to x. Okay? So this and this, remember, they are equivalent to each other. They mean exactly the same thing. But it's probably going to be easier for us to define the derivative of this. So we're going to find the derivative. Okay, find the derivative, but we're going to do it implicitly. Okay, so we start with e to the y is equal to x, and we know that the derivative of e to the y is going to be e to the y. But I have to take into account that the exponent here, y, represents some unknown function of x. So I have to include, okay, using the chain rule, I have to include the y primed, okay? Now, on the right-hand side, the derivative of x is going to be equal to just 1. That's easy. So, y primed, if I solve for it here, y primed is going to equal 1 over e to the y. But I know from up here, this form of the expression right here, that e to the y is just equal to x here. So I know that y primed is simply going to be 1 over x. And there it is. That's the rule that I'm looking for here. So, and I'm just going to wrap this up really, really quickly here, then we'll look at some examples. But just to give you the rule here, therefore, if y is equal to the natural log of, let's call it u for right now, okay, where u is some function of x, okay, then y primed is going to equal 1 over u multiplied by u primed. Okay, and there it is. There is our rule for taking the derivative of the natural logarithm. So now let's take a look at some examples of how to apply that. Okay, so here we go. So let's take a look at a couple of examples here. So find the derivative of y is equal to the natural log of x cubed. And now bear in mind that x cubed is within the logarithm here. So one way that you could approach it is to do it like this. Y primed is equal to, well, let's apply the rules that we just looked at here. So the derivative of the natural log will be 1 over the argument. So this will end up being 1 over x cubed. And then we're going to multiply that by u primed, the argument primed. Well, the derivative of the argument here will be 3x squared. So I've got an x cubed in the denominator, and I've got an x squared in the numerator. Okay, well that is going to be equal to 3 over x. I can cancel the x squared, or the two factors of x here with the two factors of x down there. Now I can do that so long as x is not equal to 0. But that particular restriction is already implied by the fact that I'm taking the natural logarithm of it. It couldn't equal 0 anyway, because that is excluded from the domain of the logarithmic function. So there we go. Y prime is equal to 3 over x. Or another way that I could have approached this is to realize that this is a logarithm and I can take advantage of that. So instead of going to y primed right now, I'm actually going to utilize our rule of logarithms. I'm going to bring that 3 out front. So 3 multiplied by the natural log of x. And now y primed is going to be 3 multiplied by the derivative of that natural log, which I know is going to be 1 over x. And then because the argument is just x, when I multiply by the derivative of x, I'm just multiplying by 1. And so this can be rewritten as, again, 3 over x, which is awesome. Same thing. Let's take a look at another one here. Y is equal to the natural log of x plus 5 multiplied by 3x minus 2. Okay, well, one way to do this might simply involve just taking the derivative of it right away here, which would mean, okay, actually what I might do with it, sorry, before I jump into doing it that way here, what I might do here is simply expand that out first. And that would give me, what is that, 3x squared minus 2 plus, what is that, plus 15. So that's going to be plus 13x minus 10. Expand that out here. And then when I take the derivative, that's going to be 1 over the argument. So it'll be 1 over 3x squared plus 13x minus 10. And then I would multiply by the derivative of what's inside there, what the argument is. And that derivative of 3x squared plus 13x minus 10 will be 6x plus 13. And so just writing those together, really more than anything else, this becomes 6x plus 13 over 3x squared plus 13x minus 10. So that's one way to do it. You don't have to do it that way. Another way that you could do this, okay, would be to once again make use of the laws of logarithms. Now this is why I wrote it out like that, by the way. So you could expand that out, take the derivative, or realize that this is going to be equivalent to the natural log of x plus 5 plus the natural log of 3x minus 2. Okay, that multiplication within a logarithm can be rewritten as addition between two separate logarithms. And so now when I take the derivative of the natural log of x plus 5 is going to be 1 over x plus 5 multiplied by the derivative of what's inside here, which in this case is just going to be 1, plus 1 over 3x minus 2, and then again multiplied by the derivative of the argument, and then the derivative of 3x minus 2 is just going to be 3. So I've got 1 over x plus 5 plus 3 over 3x minus 2. Now, just to show that this does work here, I'm going to put these together. My denominator here is going to be x plus 5 multiplied by 3x minus 2. This is going to be 3x minus 2 here, plus 3 multiplied by x plus 5. And hopefully you're following what I'm doing here. I'm just, to get a common denominator, I'm just multiplying those together. So if I have to multiply x plus 5 by 3x minus 2, I do that to the numerator and denominator. And if I have to multiply 3x minus 2 by x plus 5, I do that to the numerator and the denominator. So my denominator here, and I've already done that, I already know that that's 3x squared, okay, plus 13x minus 10. But up here, this is going to be 3x minus 2, that's that first numerator, plus, now I'll distribute the 3 through, 3x plus 15. And then there we go. 3x plus 3x is 6x. Negative 2 plus 15 is going to be plus 13 over 3x squared plus 13x minus 10. So there you go. It works out to be the exact same thing whether you apply the rules of logarithms or you don't. It's all good. Okay, now I just want to take a moment here and just point something out here that if it hasn't kind of occurred to you at this point here, there is a bit of an issue here. I just want you to remember that earlier in this series of videos here, I did point out that when you're taking the derivative, the domain of the derivative should be a subset of the domain of the original function. In other words, when you take a derivative, remember that the derivative is identifying the slope of the tangent to the curve, okay? But you can't have a derivative, you can't have slopes where there is no function. Now watch what's going on here. Okay, if I start off with y equals the natural log of x, notice that the domain here is going to be x is greater than 0. But when I take the derivative, I get 1 over x. The domain of this is going to be x cannot equal 0. But I am allowing negative values. I can certainly do 1 divided by a negative value. That's totally fine. I don't care about that. But I can't plug a negative value into this natural logarithm. So I'm running into a bit of an issue here where actually when I take the derivative here, the domain of my derivative is larger than the domain of the original function. In other words, I'm finding slopes that don't correspond to this particular function here. Now, to fix that, what you'll often see mathematicians do here is what we'll do is we'll come back here and we'll put absolute values around that. So that now the domain, we can fix that, and the domain here becomes x cannot equal 0. That's the only value that now no longer works. Okay? Now, if your teachers are like me, at this stage in the game, I'm not too worried about that. I'm really just more interested in students right now recognizing the rules of the derivatives and applying them properly, getting that algebra right here. This is something that I want them to think about, and I want this to kind of be percolating in the back of your mind here, because it is going to become an issue later on in the next chapter. Okay, I'm not going to be such a stickler about it right now, but I do want you to be aware that something weird is going on here and that you really should be looking at the absolute value of x, or at least being very cognizant of the fact, okay, that the domain here of the natural log does not match up with the domain of its derivative automatically. Sometimes I got to play with that a little bit for that to make sense. Okay, let's look at another concept here. Okay, so now we're going to finish this off here. We're going to go right back to where we started here, because now we've got the tools. And we're going to take a look at the derivative of y equals b to the x and y equals the log base b of x. Now, getting the derivative of the log base b is actually going to be quite straightforward. We're going to attack that the same way we did with the e to the x. But this is the one that's the issue here. So again, and I know I've said this a few times already, recall that if y is equal to b to the x, we've already looked at this, then the derivative is, again, b to the x, but now multiplied by the limit as h approaches 0 of b to the h minus 1 over h. And that is a little ornery to work with, okay? You'd have to start going into your calculator and fiddling around with it to make that work here. However, there is a cute little shortcut here that we can take here, something that we can introduce. So note that this is true, okay? That b, and you might have to just stop and think about this for a little bit, but the base b can be written as e to the natural log of b. Okay, I want you to think about your laws of logarithms. So remember here, okay, over here as an aside here, that if you've got the log base a of a to the x, that is equal to x. That is really the rule that we're taking advantage of here. This is e to the log base e of b. So that's equal to b. Now, you might look at that and think, well, okay, great. Thanks for that. You've made that more complicated than it needed to be. Yeah, but at the same time, we've made it a lot easier. So, therefore, if I have this as y is equal to b to the x, I can actually rewrite this as e to the natural log of b to the x. So all I do is I replace the base with this e to the natural log of b. Now, when you've got a power of a power, you just multiply the exponents together. So this becomes e to the x natural log of b. Because remember, the natural log of b is just going to be a number, not a big deal. And so that now, when I take the derivative of this is now an exponential function of the form that I'm already familiar with. And I know that the derivative of e to some exponent is going to be e to that exponent, multiplied by the derivative of that exponent. That's because of the chain rule. Well, x is my variable, natural log of b. That's just my constant. So I'm going to multiply here by the natural log of b. And bear in mind what we've just said here, e to the x natural log of b. Look at that little train of equalities here. I know that this is equal to this. So I can replace that now with this expression right here. So the derivative of b to the x is going to equal b to the x multiplied by the natural log of b. That is what this is equivalent to. So it's like, oh, the limit as h approaches 0 of b to the h minus 1 over h, that is simply the natural log of b. Yeah, that's it. Perfect. So now just to summarize that, make sure that this is clear. So in general, if y is equal to, let's say, b to the u, okay, where u is some function of x, whatever, then y primed is going to equal b to the u multiplied by the natural log of b, and then this will be shoot. I don't know why I did that. This will be multiplied by, u primed. Okay, because of the chain rule. And so there's my rule for taking the derivative of exponential functions. Now, before we get into some examples here where we do this, I tell you what, let's quickly take the derivative of a logarithmic function where the base is something other than e. So now, consider y equals the log base b of x. Well, what I might do here, like I did before, is convert this to its exponential form. So that's going to be b to the y will equal x. Now I know how to take the derivative of this. I'm going to do this implicitly. So therefore, when I take the derivative of this is going to be b to the y, b to the y, I was going to put that natural log at the end here, but I'll put it right here. So the derivative of b to the y will be b to the y multiplied by the natural log of b, and then multiplied by the derivative of the exponent, which will just be y primed here. And that is going to equal 1, the derivative of x. And so now y primed is going to equal 1 over b to the y natural log of b. And now let's think about that. We already know that b to the y is equal to x. And so the answer here is 1 over x natural log of b. Isn't that interesting that that is the way that works? So when you're taking the derivative of an exponential function where the base isn't e, you treat it the same way. The derivative of the exponential function is itself multiplied by the natural log of its base. On the other hand, if you're taking the derivative of the log base b of x, it's still 1 over the argument, but then you're going to divide by the natural log of that base. So let me write that out as a rule here. So up here, so if y is equal to the log base b of u, and once again where u is some function of x, then y primed is going to equal 1 over u, natural log of b, and then you're going to have to multiply this by u primed. And that's your rule for taking the derivative of a logarithmic function where the base is not equal to e, where the base is not equal to e, some other number. Let's just take a look at a couple quick examples and then we're good. Okay, so let's just take a quick look at a couple of examples here, and we're not going to go to town on this one. I'm just going to show you a couple of examples because it's really the same thing over and over again. Here we've got two functions multiplied together, so we have to apply the product rule here. So the derivative of x squared is simply going to be 2x multiplied by the log of x, okay, plus, and now we're going to take the derivative of the log here, but notice that this is the common log. Okay, so got to think about this. What's the base if it's not written? The answer is the base is going to be 10. So this will be the first function, x squared, multiplied by, well, the derivative of log of x is going to be 1 over x, natural log of the base, which in this case is going to be 10, and then multiplied by the derivative of the argument. In this case, that's just going to be equal to 1. Now, there's not a whole lot we can do here to simplify this. I mean, you could, if you really wanted to, I suppose you could move that 2 up as an exponent here. You could move actually the 2x up as an exponent, but that's really neither here nor there. You're just moving things around. So you can write that as 2x log of x plus, here though, you might cancel out the common value of x, so this becomes x over the natural log of 10. It's probably about as good as it's going to get here. Now, again, bear in mind here that I can cancel out those x's here so long as x doesn't equal 10, but that's already an implied restriction on the domain because of the log of that variable x there. Here, for this one right here, similar sort of a pattern here. The derivative of my exponential function is going to be the exponential function multiplied by the natural log of the base. Okay, so there's the derivative of the exponential part of this. Now I got to take advantage of that 2x here. The derivative of 2x is simply going, wow, I kept doing it. Sorry, I got to take the derivative of x squared, and the derivative of x squared is going to be 2x. Now, in this particular case, though, there are a couple of things that we might do here. Now, first of all, I'm going to move that 2x out front. So this becomes 2x, 2 to the x squared, multiplied by the natural log of 2. What I might do here is a couple of things. I might take that 2 and multiply it by this 2 to the x squared. This is 2 to the 1, x, 2 to the x squared. Well, what do I do if I multiply powers where the bases are the same? Well, I add the exponents. So you might write it like that. Or maybe what I do is I come over here and instead of taking the 2 and combining it with that power, maybe what I do is I bring it into my logarithm, move it up as an exponent on the 2 there, and so this becomes x 2 to the x squared multiplied by the natural log. Well, if I'm moving 2 up as an exponent on 2, it becomes 2 to 2 squared. Just make that the natural log of 4. So either one of those are correct, and you just have to pay attention. Where we might get students like on a question like this is in a multiple choice. If I give you an expression like this and say, which of the following is the derivative, you might not see that as an answer. So you're going to have to figure out, well, what have we done to change our answer from this, just the result that you get from directly taking the derivative, and these ones that you get when you algebraically manipulate it. So something to watch out for. But at this point right here, I'm just going to end it here, mostly because the laws of derivatives haven't changed. All I've done is added one more little piece to it. That's it. So just be aware of what happens when you're taking the derivative of a logarithm or you're taking the derivative of an exponential function.